Thanks for coming to my talk. My name is Tanmay Shankar. I'm a first-year student at the RI, and today I'm going to be presenting some of my work on reinforcement learning via recurrent convolutional neural networks. This was something I did during my undergrad, and I did this with Professor S.K. Dwivedi and Professor Prithvijit Guha at the Indian Institute of Technology in Guwahati in India. And what this framework basically does is takes the properties of something like recurrent conv nets and sort of infuses it or wraps it around traditional reinforcement learning frameworks. And what this lets us do is to provide a sort of way we can make the best of both worlds of these properties, and that's what we really want to do. We want to have an intuitive sort of setting like reinforcement learning with the trainable, learnable properties of a recurrent conv net. And so just so I get an idea here, how many people here are familiar with reinforcement learning? Okay, that's good. And right, so to start off with, this is a sort of overview of what I'm going to be doing. I will go into each of these in detail, and if at any point you have any questions, please do feel free to stop me. Right, so to get, just to make sure we're sort of on the same page, reinforcement learning is a field that deals with how to choose the optimal set of actions for an agent in an environment. It's formulated typically as a Markov decision process where you have a state S belonging to a state space. You have actions, and in this work I'll be considering a discrete grid world state space where you have a 50 cross 50 grid, and your actions simply signify moving up, left, right, down, or diagonally in one step. And there's also the notion of this transition model, which dictates the dynamics of your system, which says, given that I'm in state S and I try to take action A, what state do I end up in and with what probability? And similarly, you also have a reward function that's a sort of scalar value that you're trying to maximize. And there's also sometimes a discount factor, which basically says future rewards are much more weighted less than the immediate rewards that I'm going to get. And what we have is this value function, which is really the expected reward over time. So until some finite horizon t, and we will be considering the finite horizon case in this work, we're trying to maximize the sum of all rewards until that finite time horizon. There's also something called an action value function, which is basically the same thing, except that it says what happens if I, from the state, take action A and then act optimally. And so reinforcement learning traditionally has been bifurcated into these two classes. One is model-based RL and the other is model-free RL. Now the model here refers to the MVP model, which is sort of quantified by the transition model, which I talked about, as well as the reward function. And model-based RL really says, if I have these two values, if I have my reward function and my transition model already, acting optimally is simply a question of planning with these models. So what I really want to do is estimate the model first, either by counting in terms of learning the transition model and something like inverse reinforcement learning in the case of trying to learn the reward. And then what I'm going to do is just plan with this. And model-free approaches, which have sort of gained momentum in the recent years, what they try to do is learn these Q functions directly. And you'd have seen deep Q networks, which I will be talking about a little bit. And also you have things like policy gradient methods, and these methods really don't try to approximate the underlying model. They don't try to estimate it. They just say, given a set of inputs or states or observations, what's the action I should take? They sort of treat it as a black box. And that's exactly what deep reinforcement learning does. Well, most of deep reinforcement learning. They use deep neural networks to either approximate Q values or the policies directly. And by policy, I mean the set of mappings from states to actions. Now, one famous work you've all heard about is the deep Q networks and its infinite variance from DeepMind and Berkeley, and there are a bunch of other places. And you also have these things called policy gradient methods, which basically try to parameterize your policy using a neural network and then move that policy based on trying to maximize the reward that you're going to get. And here, as I mentioned, they take states or raw observations as input, and they output the Q values or the choice of action. And they have a bunch of tricks that I'm not going to get into right now, but it works really well sometimes. For those of you who've seen the DeepMind's paper on playing video games, it's insane. Like, they play it better than half of us would. And really what's going on is they have an input, they have some black magic system, and then they have an output. And this is some criticism that often comes to deep methods or deep learning methods, that you are trying to sort of let the system learn everything on its own in an attempt to generalize performance across different tasks. But it's very hard to intuitively understand exactly why the system's making a particular set of actions or how exactly it's working. And they often ignore any underlying task structure. This is a consequence of trying to generalize across tasks. But it also means that if I want to personally interpret what my algorithm is doing, it's very difficult. And this is exactly one of the problems that we want to address in this work. We want to go back to a more model-based reinforcement learning framework where we are exploiting this structure, this rich MDP structure that's already present, and we're going to use that to make optimal decisions. And what we're going to do is, we're also saying that learned models of the transitions and rewards are much more transferable. So for example, if I learn something in one domain, I want to be able to apply it to the next domain. And rewards and transitions are about the most transferable things that you can get in a context of reinforcement learning. And also, one sort of deterrent from model-based approaches is that you have to plan once you estimate these models. You can't just use them directly. But we're going to come up with something that sort of builds on the advantages of the first 2 points here and tries to reduce the cost of the third point here. And how we're going to do that is, what we're trying to answer is whether we can really harness the power of these deep networks, which are which can be really good at solving these tasks by simply training them or running back propagation through them, with these very classical reinforcement learning solutions. And we want this to be as intuitive and as natural as possible. And to that end, as many of you might have guessed, from the title of my talk, the answer to this question is yes, we can, and that's what I'm going to be presenting. So what we're trying to do is create a representation of these reinforcement learning solutions within a nice, deep network architecture. And what this lets us do is connect explicit steps of solving either MDPs or partially observable MDPs with the elements of a recurrent convolutional neural network. And this representation sort of inherits those properties of that recurrent convnet, and that means we can use backpropagation to train it. Now, sort of to formalize exactly what we're doing, we're defining 3 networks in this work. The first is the value iteration RCNN. I will refer to it as VI-RCNN for short, in short. And this basically computes value iteration in an efficient manner, and it also reduces the cost of replanning, which is the cost associated with model-based approaches traditionally. We're also defining a belief propagation RCNN, which primarily propagates beliefs of state in partially observable settings. And we're going to use this belief propagation RCNN to learn transition models of the MVP. And finally, we define the QMDP RCNN, which implements the QMDP approximation, for those of you familiar with it, and helps us select optimal actions in the partially observable setting. And finally, it lets us learn the reward associated with the MDP in a learning from demonstration via inverse reinforcement learning setting. Now, coming to the value iteration RCNN. First, a sort of run through of value iteration itself. We're using dynamic programming to sort of calculate this value function that I mentioned earlier. And this comes in the form of the Bellman update equation, as you can see here. Now, what this basically does is, on a sort of abstract level, it diffuses the reward over the state space. So if you look at a reward that looks something like this, what it's going to do is it's going to spread these rewards out into the surrounding areas. which will end up looking something like this. So you can see as I iterate over time, it sort of spreads out this reward. And I'm just going to go through that again for you. And what you can see here is these little arrows indicate the policy that I'm going to follow. They indicate the direction in which I should move to reach the optimum goal location. And yeah, you can also see here, I guess, that in some of these areas, the direction of the policy is pointing downwards, which is wrong since there's a much higher reward like in the center. And slowly, I mean, you can see that this field expands out and pushes and makes those arrows pulled into the center. And so what we really want to do is to represent this value iteration in the form of a recurrent conv net. And the first step to that is showing that this is in some way a convolution, or we can represent at least part of it using a convolution. And so you consider that term, the second term in the Mellon update, and it looks something like this. And for this 2D state space that we're considering, I can simply represent this sum over all states as a sum over indexes x and indices y. Does that make sense? So it's just a sum over some p and q, which represent the sum along x and y axis. And what I'm going to do then is, for a real robot, you often have some limitations in the actuation capacity. So for example, if I'm a robot, I can't move all the way to the other side of the room in one step. There's only some finite sort of neighborhood in which I can move. And this lets us define some sort of W neighborhood within which the transition probabilities or the transition model has some some finite values. And of course, outside this neighborhood, I'm saying that there's a zero probability of me transitioning. And the second assumption that we make is sort of spatial invariance of the dynamics. And why this is valid is if you consider something like a differential drive robot, a wheeled robot on the ground, it's going to behave in the same way if it were here as opposed to if it were outside in the corridor as opposed to if it were on the other side of the room. Now, of course, I'm neglecting things like, say, friction on the carpet. You might say if it's outside, the sensor might not work, but anyway. So we're going to stick with this simple assumption of saying the dynamics are spatially invariant across the state space, meaning it behaves the same way across the state space. And if you notice, sort of these two assumptions lead up to what we're going to do. We're going to fiddle around with this equation. And because we assume these two, we made these two assumptions, we can now say that this W neighborhood, this sort of restricted neighborhood, is centered around where the robot is at the moment. So the W neighborhood is centered around S prime in this case, which is over here. And so what that lets us do is convert that sum into a sum from one side of the neighborhood to the other side of the neighborhood. And this term is pretty much the same, but it says, since we're centering it around S dash is indexed by I and j, so we can sort of represent that sum up above there by this term. And another little fancy trick that I'm going to do, I mean, this was the same equation. What I'm going to do is simply define a flipped transition model. What that means is I'm going to take my original transition model and flip it both along x and y. And what that lets me do is convert the I plus u and j plus b that I have there to an I minus u and j minus b there. So really what this is doing is a bunch of indexing changes and changing the sum, what I'm summing over, but it really represents the same equation. And now you'll notice that this term is basically the convolution of t bar and v. So now what we have is this really neat representation where we have a convolution of these two terms followed by an addition of a sort of fixed reward term, since I'm assuming my reward is already given. And then I'm taking the max over all actions, which is exactly the same as what I did in value iteration, except now this kind of looks, for those of you who guessed it, like a convolution network. We have a convolutional stage, we have a fixed bias stage where I'm adding a sort of constant weight, and then we have something that looks like max pooling, except that it's not really spatial pooling, it's over the actions. So it's a pooling through depth in some sense, or the action channel if you prefer. And what this looks like, so I mentioned there are 4 stages. And of course, value iteration itself is an iterative process. So you can think of this as recurrence. Since I'm feeding the output of the network at one time step as the input to the network in the next. And what this looks like, and this should really give you an idea of what's going on, is I have an image which is really my value function. I'm convolving it with a set of transition filters, and I'm adding this reward here as a fixed bias, and I end up with something that looks exactly like my Q values of an MDP, and then I'm simply taking the maximum over them at every pixel or at every state to end up with the value function at the next step. And then I'm just really iterating through this process. Now the really neat thing about this is that this is implementing the same value iteration, of course, but I've defined these convolutional transition filters which directly correspond to the transition model probabilities. And of course, each action is represented by its own filter. And this sort of one-to-one correspondence is very different from what you would see in a convolutional network, where you need all your filters together to be able to detect something. But here you have one filter corresponding to one action which we're going to make use of later. But the entire thing is differentiable. That's the main, that's the really neat thing about this. You can backpropagate straight through this, learn either the transition models or the reward function, and then use them to plan. So this representation really has led up to something where we can learn these things rather than providing them by hand at first and then sort of plan with them. And so if you remember, we encoded the spatial invariance of the robot, and this is really nicely captured by the lateral parameter sharing that confidence enjoyed. So so these are just some sort of insights into how you should think about the rest of the things I'm going to propose. In case you want to look at that diagram again, just for a second to sort of let it sink in. Right. And just a second. Right. So that sort of leads us to think that, well, we did this with value iteration, but can we do the same thing with belief propagation? So in partially observable environments, just to sort of summarize what the belief propagation RCNN is going to do, it's going to implement the Bayes filter in its forward pass and propagate sort of beliefs of state. And in the backward pass, we're going to learn transition models. We're going to use backpropagation to learn transition models. And so in partially observable environments, you don't often have access to the state itself. Rather, you have some set of observations from which you're trying to infer the state. And you don't actually get the state itself, you're inferring some belief of state. So you have a distribution over which you think your robot's going to be. And this is, of course, in tune with some observation model which says, and these observation models can be extremely varying. So either I can have like a camera image that's fed into my robot as a state estimate. But here we're going to stick with a simple observation model that says, if my state is x and y, I'm going to observe a noisy state estimate that's somewhere in the neighborhood of x and y. And we need accurate beliefs in order to take optimal actions. Right? If I don't know where my robot is, I don't know what action to take. Now, really what we're going to do is say, I'm going to use the Bayes filter, which is a very traditional sort of filtering technique for propagating beliefs. And so this term here represents the motion, this term here represents the motion or prediction step of the Bayes filter, and the other term, which is this one, represents the correction step given an observation. And in sort of one equation, when you put these two together, it looks something like this. And just as we had done with the value iteration RCNN, we're going to fiddle with the math a little bit and represent it in as a convolution for the motion update and a element-wise product. Do you all actually understand? Do you want me to explain this again? It's the same math that we did with the value iteration thing, except we're doing it as a convolution of transition model with beliefs rather than just the value function. And right, the second step, since we considered a sort of simple observation model, the second step you can kind of think of as an element-wise product of the observation model with this term over here. And this represents the element-wise product, where I'm simply just masking my intermediate belief with the observation model. I can go back into detail in this, but I'm going to move on right now. So what this really looks like is this equation where I have one stage which represents a convolution, and the second stage representing an inner product. And this eta here is just a normalization factor. Right, so again, this might look really complicated on the face of it, but what I have is a belief at a given time step, which I'm going to zero pad, just so that the dimensions sort of work out later. And then I'm going to convolve this with one of the transition filters. So if I'm going to take action A at time t, I pick up the corresponding action filter from the transition model, and I convolve it with this zero padded belief. That gives me my intermediate belief, and then I simply, this is just a prediction of the belief. Then I correct that belief with an inner product of the observation model to give me my final sort of belief that I'm going to, that at the next state. You know, that's the belief of where I think my robot's going to be at the next state. And so if you ignore the sort of lower part of this network right now, what would originally happen in a forward pass is I just take this belief state at the next time step and feed it back as the input. And then I keep rolling this over time, and I have a way to implement my base filter, right? The interesting thing is, if I have some sort of world model,
yeah, I'm just wondering, like, what is the belief? So the belief is some sort of image, right? That's why you're doing
yes.
So what would it? Is it like your belief of the value function, or
no?
what?
It's a belief of. It's basically the probabilities of the robot being in a particular state. So for the grid world, if I have a really high probability in the center, it means I think my robot's over there. Yeah. And right, so when I'm sort of, if I have a world model that I'm sort of using to, say, play a video game, then this world model really represents the simulation or the simulator. And what I'm doing is I'm providing it a set of actions, and it's giving me a set of observations, right? And from there I can sort of retrieve a target belief. And what this target belief is really a one-hot encoding of the observed state. So I mentioned that the states are basically, the observations are basically a noisy estimate of state. So I say, whichever state I observe, I'm going to pretend that that's my belief. Which is slightly, it's an assumption, but the really cool thing is that when I do sort of encode this as my belief, or the target belief, what I want is that my network outputs a belief that is as close to this target belief as possible, right? And then what I can do is simply take the the least square loss between these two, and then backpropagate it through the network to sort of learn these transition filters. Does that make sense? Right, and yeah, so with regard to training it, the filter weights, as I mentioned, correspond directly to the transition model. And here you'll actually see where I use the fact that I only need one of these transition filters at a time, since I'm only trying to take one action at a time. So, and I want, like I mentioned, we want to learn a belief. We want the network to learn a belief or output a belief that's as close to the target as possible. And we simply minimize this loss, which is basically the least square loss between those two. Yeah.
Is there any difference between the target belief and the observations? Like, they're both.
Between the observation model and the target belief?
Yeah.
So the observation model, which is inside the simulator, really represents it represents the noise with which I'm going to see some particular observation or a particular state, whereas the target belief is really just saying, if I observe state, x naught, y naught, I have a belief of the robot being there with probability 1, and everywhere else is 0. Right? Thanks for clarifying that. That's a good point. And right, and obviously, since my transition probabilities are probabilities, they have to satisfy the condition that they sum to 1, and they lie between 0 and 1. And so I just encode these into the loss function with some penalty terms in addition to this loss. I mean, in addition to the least square loss. And really, if you think about it, the input that it takes is just a sequence of choices of actions and the observations that it get from the simulator, right? And the outputs are, the targets are this one-hot encoding of the observed state. My outputs are the belief over time. And there's a pretty important trick that I use here called teacher forcing, for those of you who are familiar with it. It basically says, since my initial transition estimates are really uncertain, if I propagate this output back into the input when I'm training it, the thing is going to explode. Like it's going to become really unstable because I'm just increasing uncertainty in the system. So instead what we do is we say, hey, I have an approximation of my belief at every time step. Why not I supply that as the input to my network? So this sort of happens in a rolling fashion where at every time step, I take my target, feed it as the input, predict a belief, minimize the error between the belief and the target, and then feed the target back. So this is how we sort of train the network. And this is also a form of target recurrence. Basically, I have the target, and the target is what is recurrent in time. So really what we did was to propagate these beliefs of state using a simple Bayes filter in partially observable environments. And that was the forward pass, whereas the backward pass really learns the transition model of the underlying NDP simply by gradient descent or backpropagation. And coming to the QMDP RCNN, which is sort of the final network that I'm proposing here, it says that, the VI RCNN gave us these optimum value functions and optimum policies, and the belief propagation RCNN gave us a nice belief of state. But in a partially observable setting, I still don't know how to choose actions. Because the policies that I generated from the VI RCNN were for an observable case, where I had access to my state directly. So what we need to do here is, can we use these two networks together to give me an optimum choice of actions in a partially observable setting? And that's exactly what the QMDP RCNN does. It sort of fuses the outputs of each of those networks respectively. So we treat the output of the VI RCNN as those Q functions, which were in blue, I think, if you remember the diagram, and the belief propagation RCNN as the belief of state. So we want to fuse these two together to get our action choices. And what the QMDP RCNN really does is, again, as I mentioned, choose optimal actions in a partially observable setting. But the cool thing is that it learns rewards when you backpropagate to it. So given a set of demonstrated trajectories, if I'm driving around my robot in a simulator, the QMDP RCNN learns the reward that I was trying to maximize by backpropagating through this network. And so how we're going to fuse these two terms together is really taking an expectation over the Q values. So for those of you familiar with the QMDP assumption, it defines a set of belief space Q values, which are really saying, if I believe my robot's in this belief, in this particular state, what is the expected Q value that I'm going to get? And this is just basically, so if I have 8 actions corresponding to each direction, this is a set of 8 values, right? So I have a belief, and I have a set of 8 sort of Q functions, or 8 Q values for every action. And I just fuse these two together using this sum over an inner product. And that leads to my Q of BS of A. You can also, just Q of BA. Think of it like that. And my optimal action is just simply the maximum of these values. Because it's the maximum of expected Q, right? So in this case, we're going to take the softmax over these actions because we want something that's nice and differentiable. And the softmax is typically a much smoother way of taking these actions, or preferring one action over the other. So here, like I mentioned, we have a set of 8 values, and then the softmax is really the maximum, the value with the maximum of this term. And this is a typical Gibbs softmax that you've seen neural networks. And so really what we've done is we've taken the BIRCNN and the BPRCNN and put them side by side, and then in front of them we've said, we're going to take this inner product and then a sum of the beliefs and the Q values, and then we're just going to take the softmax of that. So that says, the Frobenius inner product really just refers to the sum, and then, an inner product and then a sum. And the softmax refers to taking the softmax over all actions. And this is what it looks like when you put these two together. So in red here you have the BIRCNN, exactly what we drew in the previous sort of a bunch of slides ago. And here we have the BPRCNN, which is also exactly the same as we drew before. And what we're doing here is we're really just taking the inner product between these beliefs and those Q values, and then taking a sum over each state, overall states of these values, and we get an 8-bit long vector. And like I mentioned, we take the softmax and we end up with a set of actions that the network thinks the agent should take. So this is perhaps maybe one of these actions has a much higher value than the others, so we say, okay, that's the action that we want to take. And as I mentioned earlier, we were talking about demonstrating a set of trajectories for training. So yeah, I'm going to just go forward and I'll come back to that item though. So we have a learning from demonstration setting where we want to learn the reward. And how we do this is, So we want to learn a reward that really explains these expert trajectories, or that says that given this reward, my expert trajectories are now optimal. And basically what we want to do is the actions that the network suggests should match the expert actions as closely as possible, right? That's the sort of high-level way of looking at it. And so what we do is we have these two 8-bit long vectors. One says this is what the expert actually took, and this is what I'm suggesting. And I take the cross entropy loss between these two and say that this is the loss function that I want my network to minimize at every time step. So yeah, like I mentioned, the input is again just a set of actions and observations. And the targets now, instead of a one-hot encoding of the belief, are the one-hot encodings of the action that I take. Which means it says, if I took action 3, it has value 1 at index 3 and 0 everywhere else. And to sort of come back to this network, these are the targets that I have, which are basically the demonstrated, the actions that my demonstrated agent took, or the expert took. And these are the output actions. And now what I do is I just take the cross entropy loss and then backpropagate it to update my reward. And this is, it's pretty cool if you think about it. The fact that just given observations and action choices, I'm able to learn and reconstruct a reward that explains my robot's trajectories as optimal. And yeah, we already went through this. And another trick that I didn't mention was that since we're trying to plan as well, we ultimately want to use this reward to generate those that optimum policy as well. And if you look at this network, it does have this sort of value iteration embedded in it. And we found that if you only do that recurrence once in every, say, 10 steps or once in every 20 steps, as compared to every iteration of the belief propagation, this helped the system sort of stabilize a little bit. But yeah, that's a simple trick. So basically, another interesting thing that you can note is when you work out the gradients of this, it looks something like this. So just to remind you, this is the target action, this is the action that the network suggested, and this is the belief of state. And the reward gradient really works out to these two simple terms, which is basically saying this is the extent to which I want to either positively or negatively reinforce my choice of action. Which is saying if I take the right action, that's good, I'm going to reinforce that action by a small amount. And the belief term here really directs this entire reward update to a small area of the state space where I think my robot is. And why that makes sense is because if my robot's in the corner and it takes a particular choice of action, I'm saying, okay, maybe that action choice is relevant to when the robot's in a corner. So the belief term here really sort of acts as kind of an attention mechanism, if you think about it, that directs the rewards to a specific region of the state space. And like I mentioned, the y hat minus y term defines the extent to which I want to give feedback to the agent. And and that's pretty much most of how the training really works. Yeah.
So is this an actual analytical gradient of the loss, or are you setting it as the gradient?
Oh no, this is the app. Like when you work out the map,
It's
this is
the
what.
actual.
Yep. It's pretty interesting that the gradient works out to a term this small, I think, but it really, I think it follows from the QMDP assumption. So the Q values are really just linear in the reward. They're just some term plus the reward. So the gradient with respect to the reward here, the gradient with respect to Q and the gradient with respect to the reward are really the same. So it just becomes differentiating this function with respect to the reward, which is why it works out there. And so as with anything involving reinforcement learning and deep learning, people say, no, we want results. And you should have results. So as I mentioned, the value iteration RCNN really was making this process more efficient, making value iteration sort of faster, or doing it smartly in some sense. And what you see is by defining that finite sort of neighborhood in which I can transition, I'm saying that I don't care about the rest of the state space. I'm not going to pointlessly update the values in that part of the state space where it's not necessary. And so when I plotted the runtime of this, which is the time per iteration of value iteration, for both the regular implementation versus the implementation via the VI-RCNN, the inherent sort of parallelization of the convolution in the VI-RCNN makes this sort of orders of magnitude more faster. And what we also did was vary sort of the extent of this W neighborhood to see how much is really coming from that, how much of the speed up is coming from the parallelization of convolution versus how much of it is coming from the sort of size of the transition filters that I'm using. And just so I think I'm going to zoom out at this point and say that this work really comes up with a new representation of these algorithms. It isn't particularly creating a completely new set of frameworks. It's only representing one set of frameworks in another set of frameworks that lets you train these things or learn these things differently. And while speed is a major concern, this is not sort of the primary result that I'd like to highlight. More importantly, the results of the belief propagation RCNN and the QMDP RCNN in terms of learning transitions and rewards, I think those are sort of much more exciting, and I'll move on to that right now. Right, so here what we did was we measured, we have these two performance metrics. So basically what we were trying to do is learn the transition model for the BP-RCNN, and we also wanted to B-plan with this. We said, given that learned model, how good is the policy that we learned from this, right? And what we did was we compared the BP-RCNN with these two other methods which basically count the number of states, count the number of times you go to a state, and then maintain transition probabilities accordingly. And we also did this for a variety of settings. So if you have a fully observable case versus a partially observable case, so that refers to the first two rows over there. And we also checked out, what happens when you adapt the learning rate differently for each of these, and fiddle around with how the recurrence itself is working. And I think the main thing that you want to notice here is that, so for the partially observable case, the replanning accuracy that you get from the belief propagation RCNN sort of really outdoes these counting-based approaches. And this is sort of the main highlight of this, where it says, my algorithm can now learn these transition model values with pretty good accuracy, even in partially observable settings, which is a really big deal. Now I can, just let a robot run around and learn its own dynamics. And I can get back into the results, at this point. I mean, of the BPRCNN at this point, but I also wanted to show you the QMBPRCNN, the results of that. So just to quantify sort of when you're doing something like inverse reinforcement learning, where you're learning the reward associated with a task, it's sort of meaningless to compare the reward itself with the ground truth reward. And the reason for this is that multiple rewards can induce the same behavior, right? Simply, if I multiply all my reward values by 10, I'm still going to have the same behavior, which means that comparing these rewards themselves doesn't really make that much sense. Instead, what we want to do is we say, compared to the original policy that I had, how good is this learned policy doing? And this is like encoded by the value function of the learned policy compared to the value function of the original policy. And this is the sort of metric that we use for comparison, along with the same retiming accuracy that we had in the belief propagation RCNN. And right, so for the QMBP RCNN, we tested out with a bunch of parameters, and we say that the retiming accuracy that you kind of get across all these cases is around 65–70%. Yeah, sorry, I should have added the standard deviation values here, but yeah. But and you notice that the expected reward increase, which is what we really care about, is at around -10%, which is saying I'm doing about 10% worse than my original policy. But if you think about it, doing 10% worse than my original policy isn't that bad, especially when you consider that I could have been getting no reward at all, in which case this would have been a -100%. So doing 10% worse is not that bad at all. And if you consider this with sort of learned rewards or learned transition models from these existing algorithms, we're at -70%, -60%, -30%. So yeah, that sort of puts into context this -10% being not that bad. And we also varied this across whether you learned that both the transition and the reward, or just the transition, or just the reward. And so that's what this sort of represents. And with that, I think I'd like to summarize in saying that we introduced the value iteration RCNN, which was facial recognition, and reducing the cost of model-based approaches. And we also introduced the belief propagation RCNN to learn these transition models and propagate beliefs of state, of course. And the QMBP RCNN finally, which selects optimal actions in a partially observable environment and learns the reward functions associated with these agents. So the moral is, make model-based methods great, right? And I'm just going to take like 1 or 2 more minutes and say that, so while this is what I have been doing, some things that I'd like to extend in this work are making this apply to time-varying rewards. So if I have a system where my reward is changing over time, then I have, like if I basically stack up these QMBP RCNNs over time, you get these really nasty recurrence relationships that are like connecting all over the place. And I want to basically use this framework to learn when different rewards are important. So if I have a time-varying reward and I have a finite horizon till which I'm planning, I want to see, okay, maybe this section of the reward is important to me right now. And I'm trying to learn a weighting for that reward using a sort of stacked version of the QMBP RCNN. And with that, I'd like to conclude, and thank you once again for coming to my talk. I really appreciate it. If you have any questions, please do let me know.
I have a question.
Yep.
So somewhere like way back when, you said, I might miss this, but you said somewhere in the slides that you're learning a reward function which explains optimal objective. You said something like that,
yeah.
Right? How does it explain it? Like, what does that mean?
Okay, so, well, in inverse reinforcement learning, what you're trying to do is, given a set of trajectories, I'm trying to reconstruct a reward that says, if my reward was this estimated reward, and I planned with it, the resultant trajectories would be optimal. So the trajectories are optimal with respect to the learned reward.
Okay, so you're saying it generates, not necessarily explain. I'm just confused by the terminology explain.
So explain really here refers to if I were to generate a reward, if I were to learn the reward from it, then the trajectories that my expert agent demonstrated would be optimal with respect to that reward.
Okay.
That's what we're trying to do, which says, it's like, it's imagining it as though the expert was really optimizing this reward all along, but we didn't actually know that he was optimizing that, right?
I see. Alright, that's fine. Thanks.
Yeah, sure. Any other questions?
Yeah. With the value iteration network, the first convolutors you sort of explained as being the transition functions. Is that sort of a restriction? Like you'll only have as many convolution filters as there are actions, or can you have you have more, or does that actually?
So interestingly, there was a work that was very similar to the value iteration networks from Peter Beal and Sergey Levine at Berkeley that is called value iteration networks. And one of the things that they did was, say, in my case, I've assumed someone mapping like you said, but what they did was they experimented with a bunch of other transition filters, which basically doesn't correspond directly to the action that I'm taking. But they said that did help. They introduced some sort of hierarchical way of doing this, where you have a bunch of transition filters instead of just these 8 ones that I'm considering. And apparently that did help. I think their results in terms of replanning or how accurate they were. In my case, the motivation is more so to create an intuitive understanding of this, or something that corresponds directly with the existing framework. I don't want to add conflayers or add things that I can't explain intuitively. Right?
Did you get a chance to like visualize? Like, did the filters look like? Because if they're corresponding to like left and right, then you expect some sort of.
So that's a good question. I don't have them on this, but so for example, actually, wait, I might. Just a sec. This is a really old presentation. Right, so this is what the ground truth transition looks like for a 3x3 case, which is pretty much the simplest. And I think I have a learned one here somewhere. Yeah. So on the right are the ground truth values, and on the left are these learned values. So, which is pretty neat. Like you can see the correlation pretty evidently. You'll also notice that even when there was zero probability here, there is some sort of probability of getting this. And why that happens is in implementation, you can't really say that there's a zero probability. You add some like epsilon noise, which then the network picks up and thinks, oh, that there is a finite probability of it. But yeah, this was sort of the case across all the actions. What really excited me was the fact that it is learning something that very obviously correlates to the initial filter values, which was neat.
It's interesting that one seems to be wanting to go more left. Or maybe it'd be like some bias in the data or something.
Sure,
but that is actually quite cool.
Yep.
So coming back to your graph on the more, your approach is making it more efficient in terms of number of computations. And I don't remember, you said there were two. There was one. One of the reasons was the window that you considered. What was the other one?
So in my implementation, you're talking about this graph, right?
Yeah.
Right. So in my implementation, I implemented this value iteration by myself, and I understand that when I'm convolving things, say in a standard library, where say NumPy, for example, which is what I did implement this in, they do have some tricks to parallelize the entire thing and make it speed up. So I would attribute some of the speed up to that as well, and not just algorithmic, but yeah.
So in terms of number of computations, if your window, if let's say you had incorporated the window thing in the regular one, it would have been equivalent in terms of
actually this was with that.
The regular?
Yes,
also,
even the regular one had, like I put in, like, it said only if the state is within the window am I going to execute that computation.
So the speed up probably comes from the library used for convolution, right?
Yes, but
In terms of number of computations, it's the same.
yes, it is the number
Of
yeah.
computations.
Right. But that said, I think one interesting argument of the speed up is saying that if I let my transition filter, actually I didn't talk about this, but the W neighborhood that I consider doesn't have to be a 3x3 or a 5x5.
Mm-hmm.
In the most general case, I can just let it be as big as the image itself. And then ideally it would learn that those values are 0. Then I can prune those out and then use those to implement value iteration, which is saying I'm going to let it learn the most general case, but if it happens that those values are 0, I don't need to worry about them, which is saving me a whole lot of number of computations. That's when the number of computations really kicks in as opposed to the implementation of it. But yeah, that's a good question.
I have another question.
Yeah, sure.
If you don't mind. And the belief computation that you do, you set the target to what was the term used? Hot.
One hot. Yep.
One hot.
Yep.
Is that always a good idea or not?
That's a really good question. It isn't always a good idea. So, especially, here one of the limiting factors is the fact that my observations are in the same space as my states. So my observations are noisy state estimates themselves. But in cases where I have, say, like I mentioned, a camera image from which I'm trying to infer my state, then I think a one-hot encoding of the ability or of the observed state would not work. I would need to incorporate something more complex here. I think one thing that I could include is a sort of maximum likelihood estimate of the state over that belief, and then provide that as a target, and then repeat the same thing.
Yeah, it's just the fact that there's 0 everywhere and 1 might be too. Again, it also depends on how far you let the back propagation go, because it's never actually gonna. Are you stopping? Are you actually converging how many in your experiments? How many iterations did you